Okay. In the last video, we looked at a sphere as a constant rho surface, and we were able to then use theta and phi as parameters to parametrize that surface. That same trick works for any constant surface in cylindrical or spherical coordinates. So let's just say that we're in cylindrical coordinates, and I'm looking at r equals 2. So that would be a cylinder of radius 2, centered along the z-axis. Okay. But if I want to then describe this in terms of parametrizing it, I would say, okay, the other two cylindrical coordinates that I have would be theta and z. So usually it's r, theta, and z, but now r is constant. I'm going to map things into 3 space. In general, I get that x is r cosine theta, but now r is fixed at 2, so that's going to become 2 cosine theta. Y in general is r sine theta, but r is 2, so that's 2 sine theta, and z is just z. Okay. So I'm basically getting that r of theta z, and you can really put the order however you want. There are times when the order in which we write things will make a difference, but I'll alert you when that's the case. Okay. This would just be 2 cosine theta, 2 sine theta, z. Okay. And so let's see. If I want to get this just once, I probably want to let theta just vary from 0 to 2 pi, but I would then take an infinite rectangle. So I would let z, I can't draw infinity, but I would take this infinite rectangle, and I can sort of see what my constant theta curves and my constant z curves would be. If I hold z constant, let's say I was to hold z constant at 1. So I would get r of theta 1 would equal 2 cosine theta, 2 sine theta, 1. Well, that puts me in the plane z equals 1. That's drawing a circle of radius 2 right along the outside of that cylinder. Okay. If I were to look at a constant theta curve, let's say I wanted to look at theta equaling, oops, not phi, theta equaling pi over 2. Okay. So then I would get r of pi over 2z, and that would equal, let's see, cosine of pi over 2 is 0, so I would be getting 0 there. Sine of pi over 2 is 1, so I'd be getting 0, 2, and then z is z. Okay. So I could come to the point where x is 0 and y is 2. That would be this point right here on the outside of the cylinder. And then z can be whatever I want. I'm getting a vertical line along the side of the cylinder. And of course, for other theta values, I'd just be getting vertical lines in the constant theta half plane that corresponded to the theta value that I picked. Okay. So, kind of neat to see. Okay. Now, in spherical coordinates, if phi is constant, I know I'm getting a half cone. I'm going to hold off on showing you that one just because we're going to have several options for describing a cone, and I want to show you all of them together. But I can certainly describe a cone using rho and theta as my parameters. And in both of these systems, if theta is constant, I'm getting a half plane. And then in cylindrical coordinates, if z is constant, I'm getting a plane. Rather than using cylindrical or spherical coordinates for a plane or a half plane, there's another trick that's kind of nice for planes that I'm going to show you. And then if we needed to, we could restrict the domain of things in order to get just a half plane. Although I certainly have the option of using either either r and z or rho and phi to describe a half plane if I want to. Okay. All right, and I could even describe a full plane if I removed the restrictions. For example, in cylindrical coordinates, usually we're using those for integration, so we require r to be positive. If I don't require r to be positive, I could describe a whole plane. Okay. But there's a nice way of describing a plane. If I have a point, I'm going to just write this as r naught. Okay. So we've been writing this as a vector function that maps from a point in 2 space to a point in 3 space. I'm writing it as a vector, but we're using the same convention that we use for parametric curves, that rather than drawing a bunch of arrows when we go to graph this thing, we're graphing a bunch of points, identifying a vector with its terminal point when it's drawn in standard position. So let's suppose that this point is on my plane, and then I also have two vectors, A and B, that are parallel to that plane. So right now, the plane is essentially my whiteboard here. Okay. Well, this point is on my plane. Okay. And if I wanted to get to this point, I could start at r naught, and I could come in this direction, A for what? Let's see, that's so right about here. Okay. So I could add to r naught this multiple of A, and that would take me to here. And then I could add to that, where did I want to end up here? I could add to this a multiple of B. Notice this is parallel to B. So I could describe this point as this starting point plus some A's plus some B's. And that's going to work for any point on the plane. Okay. So I could say R of, I'm going to just introduce parameters U and V, would be R naught plus U copies of A plus V copies of B. Okay. And if I were to take a look at that, I'll just keep my basic thing up here. So if I've got the UV plane here, and I'm trying to map to this plane, which I'm thinking of is in 3 space, if I were to look at a constant U curve, so this would be like the line, let's say U equals 1. Okay. So that would take me to R naught plus 1A, and then plus some multiple of B. That would essentially, let me color code it, that would just take me to this line that was parallel to B. On the other hand, if I looked at a constant V curve, let's say that's where V is 1, so that would be R naught plus 1 copy of B plus some A's. That would take me to this line that's parallel to A. So my constant U and V curves would just be grid lines, but they wouldn't necessarily be perpendicular the way we think of when we have graph paper. They'd be grid lines that were parallel to A and B. Kind of neat to see.